Good afternoon, Prof. We are Group 7 and today we'll be sharing our project titled Predictive Modeling of Traffic Accident Severity in the United States using Big Data Analytics. Our goal was to explore whether we can use historical accident data to predict how severe an accident might be based on various situational and environmental factors. Here's our team: Jing En, Li Hui, Yifan, Fiona, and myself, Brian. We each took on a different role, from feature engineering to model design and evaluation, and we collaborated closely to integrate everything into a unified pipeline. Now, let's dive into the problem we set out to solve. Road accidents are a serious public health issue. In 2021 alone, there were over 1.19 million traffic related deaths globally. In the US, the situation is similarly alarming. This led us to our problem statement, which was: can we accurately predict the severity of a traffic accident using historical data? We focused on predicting severity from 1 to 4, where 1 means minimal impact on traffic and 4 indicates major disruptions. By doing this, we aim to provide insights that can support better emergency planning, road design, and traffic management. We used the US Accidents 2016 to 2023 dataset from Kaggle, which contains over 7.7 million records and 46 attributes. The data includes Boolean columns like traffic signal and junction, categorical columns like weather condition and time zone, numerical values like visibility, wind speed, and temperature, and date time data for when accidents happened. However, due to computational constraints, we had to downsample our dataset to 500,000 rows while maintaining the distribution of severity classes. This gave us a manageable yet representative subset for model building. So why did we choose this dataset? Firstly, it has a large scale and rich feature set. With millions of entries across the US, it captures a wide range of scenarios, from weather conditions to infrastructure. Next, it includes a severity label from 1 to 4, which is directly aligned to our classification objective. Lastly, it's publicly available and well maintained, which makes it suitable for reproducibility and future work. Moving on to exploratory data analysis, this chart shows the distribution of accident severity. As you can see, severity 2 dominates the dataset, followed by 3, while 1 and 4 are underrepresented. This class imbalance posed a challenge for our models, especially for accurately predicting the rarer but critical severity 4 incidents. We also visualized accident locations across the US. And as you can see from this map, we can see that the majority of the accidents are severity 2, as shown by the color blue, and they mainly occur around California and the East Coast, where Miami and New York are. Moving on, we also explored the relationship between accident severity and weather conditions. As expected, severe accidents are more likely to occur during poor weather conditions, such as fog or rain, as you can see in the chart here. Moving on, we tried to study the distribution of accident severity across different hours of the day. What stands out immediately are the two peaks, around 7 to 8 a.m. and 4 to 6 p.m., which correspond to the typical morning and evening rush hours. These periods are highlighted in red on the chart, as you can see. During these hours, we see a significant spike in total accident counts, especially in severity 2 and 3, which represent moderate traffic impact. This suggests that high traffic density and commuting pressure during these hours potentially contributed to increased accident risk.
Now, I will be sharing about the data preparation for our project. We faced three key challenges. For the first challenge, the original dataset was extremely large with over 7.7 million rows and 46 columns. This made it difficult to work with efficiently, especially during the iterative phases of development and modeling. To address this, we selected a 500,000 row subsample that preserved the overall feature distribution. This allowed us to balance representativeness with computational feasibility. For the second challenge, several columns such as precipitation had a high proportion of missing values. These missing entries could have introduced bias, and so we chose to drop all rows with any missing values. This ensured a clean and consistent dataset without the need for imputation, even though it slightly reduced the data size. For the third challenge, the dataset included free text fields like description, which are unstructured and difficult to process without additional natural language techniques. We removed these unstructured fields to help streamline the processing pipeline and focus on features that could be readily transformed and modeled. We then moved into feature engineering, designing modular functions that extracted richer context from raw columns. For the start time column, we derived new temporal features that could contribute to the severity of incidents. Raw datetime fields like start time contain valuable context but are not immediately useful in their default format. For instance, we calculated a binary feature called is rush hour, as the likelihood of accidents and their severity may increase during peak commuting periods like morning and evening rush hours. We also introduced real interaction features, for example, combining junction and crossing to flag complex intersections. Environmental context was added by binning weather condition from 109 distinct labels all the way down to 9 meaningful groups like rainy or clear. Finally, we created spatial features like grid let and grid longitude and calculated a traffic congestion score based on accident density within each grid cell. All of this was implemented using reusable modular functions to ensure pipeline modularity, making it easy to extend or scale later on. Our final data frame had 39 columns split between original and feature engineered variables. For our project, our target variable was severity, which is a four-class categorical feature ranging from 1 to 4. Severity 1 indicates minor disruptions, while Severity 4 represents the most serious accidents. We deliberately kept all four classes to preserve the granularity of the original labels. This choice adds complexity by turning it from a binary to multi-class categorization task, but allows us to derive more nuanced insights. This is especially in scenarios where understanding severity is critical for emergency response, dispatch prioritization, and resource allocation. Next, there were multiple categorical variables in our dataset, such as road type, time zone, and wind direction. However, categorical variables are unsuitable to be fed into our models as is. To make categorical variables suitable for machine learning, we used a two-step encoding approach. Firstly, we applied string indexer to assign each category a unique numerical index. In the example on the right, rainy is assigned 0, sunny is assigned 1, and foggy is assigned 2. We then passed those indexes into a one-hot encoder, which converted them into binary vectors. This helped to preserve category distinctions without implying any ordinal relationship. The result was a clean, unified vector that combined numerical and encoded categorical data ready for training. After preprocessing, we had 39 features, but this proved computationally heavy. Thus, we trained a random forest classifier to perform initial feature selection. We then retained the top 20 features based on importance scores, which included distance, road type, and traffic congestion score, amongst others. This allowed us to focus training on the most relevant predictors, reducing noise and speeding up model experimentation.
Hi everyone, I'm Li Hui. Now I will be sharing about the machine learning models that we have used in this project. There are two main criteria that we followed in selecting the ML models. First, we check whether multi-class classification is supported for the model in PySpark. Next, we also considered the computational efficiency due to limitations in cluster resources. This slide shows the five models that we have chosen for the project. They are naive Bayes, random forest, logistic regression, decision tree, and multi-layer perceptron. Naive Bayes offered the fastest runtime compared to all other models. However, its assumption of feature independence oversimplifies the complex interactions present in our dataset. To complement it, we use logistic regression and decision tree models for their interpretability. However, decision tree models are prone to overfitting, especially when they become too deep and start capturing noises in the training data. To mitigate this, we incorporated ensemble learning through random forest. Random forest uses bagging, which is training each tree on a random subset of data sampled with replacements. Then the final predictions are made via majority voting. This enhances generalizability of the model and reduces overfitting. While effective for modeling simple interactions, random forests may underperform in capturing complex and high-dimensional patterns. To address this, we introduced a multi-layer perceptron which leverages dense feature representations and nonlinear activation functions to better classify accident severity. Next, we will be discussing on model validation and evaluation. We split the dataset into a ratio of 70, 15, 15 for train, validation, and test set. With over 500,000 samples, this approach remains robust for our models to train and learn the feature representations. The validation set supports model selection and hyperparameter tuning, while the test set is for final model evaluation. Since we are dealing with a multi-class classification problem with imbalanced data, we need to choose an evaluation metric that accurately reflects the model's performance across all classes, not just the majority ones. The selected metric should be insensitive to class imbalance and provide a more comprehensive view of how well the model handles all severity levels, including the less frequent one. Below here shows the most commonly used evaluation metrics to measure the performance of machine learning models. While accuracy is the most intuitive to understand, it is extremely misleading in an imbalanced dataset. In our original dataset, we have near 95% of class 2 and 3 accidents and only 5% of class 1 and 4 accidents. If we rely on accuracy, we will fail to capture the severity of barrier accidents because most prediction will fall into the majority category. While precision is useful for when false positives are costly, recall is useful when false negatives are critical, and F1 scores balances both precision and recall, they still do not reflect how well the model distinguishes between classes. On the other hand, AUC, that stands for area under the RC curve, is a robust metric, especially in multi-class classification and imbalanced dataset. It evaluates how well the model distinguishes between different classes, regardless of the class distribution. AUC considers all thresholds of classification, making it especially useful when the class distribution is imbalanced. It does not favor the majority class, allowing us to see how well the model ranks severe accident over less severe ones. AUC refers to a curve that plots true positive rate over false positive rates across all classification thresholds. If the model consistently ranks positive samples higher than negative samples, the AUC will approach 1.0. If it ranks them randomly, then AUC is zero point 0.5. To measure the overall performance of all classes, we adopted the overall weighted AUC as the primary evaluation metric. We do this by computing individual AUC for each class, then multiply it with the relative frequency of the class in the dataset. And finally, we sum these values to get the final overall weighted AUC. By using the AUC, we were able to evaluate how effectively each model distinguished between all severity levels, not just the more common ones. This provided a much more reliable signal to help us identify the most generalizable model. In the end, the random forest model showed the most consistent AUC scores across the different classes, achieving an overall AUC of 0.76. This indicates that the model correctly ranks severe accidents above less severe ones approximately 76% of the time. As a result, AUC became the decisive factor in selecting random forest as our best base model, which ultimately served as the meta-learner in our ensemble approach. Apart from the overall AUC performance, we also looked into individual class AUC performances where we noticed that each model displays its own strength. For example, in the table, AUC 1 tells us how well the model distinguishes severity 1 from other severities. For severity 1, logistic regression is the best at distinguishing it from other classes compared to other models. This applies to severity 2, where random forest is the best, and so on. In terms of minority classes, which are class 1 and class 4, we found out that MLP achieves second highest in severity 1 and 4, with naive Bayes close behind. This shows that they demonstrate good sensitivity to minority classes, even though they underperform on majority classes. With the understanding of overall weighted AUC and individual AUC performances, we set the context for our meta-model architecture in the next section.
Thank you, Li Hui, for sharing how we selected our models. Now we will share how we approach model tuning. We want to boost our overall predictive performance, especially for the underrepresented severity classes, and improve the overall AUC. Each of our baseline models had shown different strengths. For instance, random forest showed strong generalization across different classes, while MLP and naive Bayes model captured patterns specific to the minority classes. Hence, we decided to implement a stacked ensemble, also known as a meta model. Rather than relying on a single model, a meta model approach allows us to combine multiple classifiers in an intelligent and adaptive way. We wanted a way to leverage the best parts of each model. Now we will be sharing the architecture of how we did our model tuning. First, we will use the validation set for model tuning. This step is crucial as it ensures that the meta model learns from the data that the base models have not seen during training. This helps to generalize the model, making it avoid overfitting. We will use the validation set on each base model: random forest, decision tree, logistic regression, naive Bayes, and MLP, which was trained on the training set. However, instead of using the prediction of the most likely class, we will extract the model's probability distribution over the severity classes, also known as soft predictions. We will collect these probabilities from each base model and stack them into one big input feature. Combining the input feature, the target variable, we would train our meta model to capture the unique strengths of each base model. We selected random forest as the meta learner, as it not only had the best individual performance in our baseline test, but it also handles non-linear relationships very well, making it the ideal candidate for combining the diverse outputs of our base models. In our final pipeline, we first use the baseline models to extract the softmax probabilities, which are then passed to a trained meta model that produces the final prediction. By stacking models this way, we were able to enhance robustness, reduce overfitting, and improve prediction. Now I will discuss the final results after tuning the model. We evaluated the performance of all the models based on their mean weighted AUC score. As shown in the bar chart, our meta model achieved the highest AUC score of 0.78, outperforming all the baseline models, and it also showed notable improvements in class-wise AUC, particularly for severity level 2 and 3. This table presents a detailed breakdown of model performance across various metrics, including overall AUC, class-wise AUCs for each severity level, accuracy, F1 score, precision, and recall. Our meta model achieved the highest overall AUC along with the best accuracy, F1 score, and recall, indicating strong and balanced performance. However, the performance gap between the meta model and the random forest is moderate. In fact, the class-wise AUCs and the other metrics are very close. Upon closer observation, we noticed that the meta model's predictions closely mirrored random forest, which likely contributed heavily to the ensemble's output. This performance similarity likely indicates that random forest is dominating in the ensemble, or that the baseline model's performance were correlated. The base learners were trained on the same feature set, leading to overlapping decision patterns. When analyzing the feature importance of the meta model, we found that the random forest and decision tree were the most heavily weighted contributors. This aligns with what we observed earlier, the meta model's performance closely mirroring that of random forest, especially for the majority classes. Interestingly, while multi-layer perceptron and naive Bayes had stronger sensitivity on minority classes, they were assigned lower weights in the ensemble. This suggests that the meta model prioritized base models that performed well on the dominant patterns in the data, possibly at the cost of underrepresenting models that were better at detecting minority class signals. A key takeaway here is that the model weighting in ensembling can introduce bias towards majority class performance, which is something to watch out for when class imbalance is a concern.
To further improve the performance and robustness of our meta model, we've identified four key directions for future work. First, we can increase the diversity of base learners. Currently, our base models were all trained on the same input space. By applying class balance sampling, using different feature subsets, or even incorporating models with varied learning biases, We can enhance the complementary signals available to the ensemble. Second, we recommend calibrating base model probabilities. This helps ensure that the softmax outputs fed into the meta model are reliable and comparable. Calibration methods like Platt scaling or isotonic regression can prevent the meta learner from being over-influenced by overconfident base models. Third, we can explore class-aware training objectives, especially in the meta model. Approaches like weighted loss functions or focal loss could help emphasize performance on underrepresented severity levels. And finally, while we use random forest as the meta learner due to its strong individual performance, future iterations could test alternatives such as gradient boosting or logistic regression to avoid redundancy and reduce overfitting to tree logic. Over the course of the project, we encountered several challenges, both technical and methodological. First was resource constraints. With over 7 million records in the full dataset, we were limited by hardware capacity and had to work with a 500,000 row subsample. While stratified sampling helped maintain representativeness, some rare patterns may have been missed. Second, class imbalance proved challenging. Severity 2 and 3 dominated the dataset, making it harder for models to learn meaningful representations of the less frequent severity 1 and 4 classes. We addressed this by monitoring class-wise AUCs, though future work could benefit from oversampling or synthetic data augmentation. Third, the ensemble gains were limited. Although the meta model outperformed individual models, the improvement was modest. This was likely due to the strong influence of random forest and the high correlation between base model outputs. Lastly, multi-class classification itself introduces added complexity, especially when balancing overall performance with minority class sensitivity. Each severity level carries different real-world implications, and model trade-offs must be interpreted accordingly. There were a few important assumptions that underpinned our modeling process. First, we assumed that the 500,000 row subsample was sufficiently representative of the full dataset. This was necessary due to computational constraints. We applied random sampling, where the large sample size and wide temporal coverage helped ensure a diverse and meaningful subset for model training and evaluation. Second, we assumed that the uncalibrated probability outputs from our base models could be directly used as inputs to the meta model. Although probability calibration could have further improved interpretability and performance, our base models produced stable and separable probability distributions, which the meta model was able to learn from effectively. Lastly, we assumed that the features selected based on random forest importance scores would generalize well across all models. These features align closely with domain knowledge, such as row types, intersection complexity, and congestion scores. So we considered this a reasonable basis for selection. To end off, here's a quick overview of our project roadmap. We began by defining our problem statement to predict the severity of US traffic accidents using a multi-class classification approach, informed by environmental and situational features. From there, we pre-processed the raw dataset and created a clean, reduced version through feature engineering, log transformations, spatial grid mapping, and categorical encoding. We then trained and validated 5 baseline models using standard evaluation metrics, prioritizing overall AUC and class-wise balance. Random forest emerged as the most robust model, but we also observed that models like MLP and naive Bayes performed better on minority classes. These insights led us to build a stacked ensemble, where a random forest meta-learner combines softmax outputs from all base models. This meta-model achieved incremental but consistent improvements across AUC, F1, and accuracy. Finally, we reflected on limitations, such as class imbalance, over-reliance on random forest, and underutilization of niche models like MLP, and proposed enhancements such as probability calibration and class-aware learning objectives. We have now come to the end of our presentation. Thank you so much for listening. We hope our project offers a practical foundation for traffic management authorities to better anticipate accident severity, enabling better resource allocation, faster emergency response, and more targeted infrastructure planning.